my talk today will be strongly correlated with what we are doing now in our laboratory in the University of Tokyo. It's correlated with the hydrogen productions because we are also conducting several research correlated with the hydrogen production, storage, and also utilizations. And today, I just would like to focus on one topic that we are doing now currently, especially for the hydrogens or clean hydrogens productions. So the title for today is correlated with the clean hydrogen production based on the chemical looping technology. So I just would like to talk in coverings both micro to and kind of like microscopic or system levels developments. So before I'm going forward for my talk today, I just would like to introduce our laboratory here in the University of Tokyo. So we are expecting that in case that you have any interest for collaborations, we would like to welcome for any kind of collaboration with all of you. And now currently we have independent laboratory in our university, so you can access the details about the laboratory, about the what topics we are doing now currently in the labs. The website is epi.is.u-tokyo.ac.jp, and currently we have about 18 students in total, and also another 4 researchers working in our laboratory. And several topics are basically being conducted now. Currently, we have several quite broad topics in our lab. So the first topic is correlated with the energy modeling, or any kind of process modelings. It covers any kind of like steady state and also dynamic state of the process simulation and also energy modelings. We are also adopting any kind of data-driven or any kind of like machine learning-based, artificial intelligence-based energy modeling, energy prediction, and also optimizations. And also we are developing several elemental technologies, especially for the hydrogen production. So it is the main topics that I would like to deliver today. It's correlated with the chemical looping hydrogen productions. And then also we are now conducting any kind of like what we call is the absorption-based hydrogen storage. But we are much more focusing on developing the structures to be used for the canisters for the metal hydride to effectively store the hydrogens. So we are adopting what we call the triply periodic minimal surface structures like gyroid, Schwartz, litinoid, or etc. And then also we are doing any kind of research with the hydrogen utilization, especially dedicated hydrogen or ammonia combustion, and also co-firing technology. And for the co-firing, also we are having international projects sponsored by Japanese governments. So we have quite big demonstration projects correlated with the co-firings of ammonia and coal for power generations. And then also we are doing any kind of what we call the industrial decarbonization system. So we are focusing on like iron steel makings and also any kind of like cement production decarbonization over there, whether in the upstream process, like we are replacing the carbon-based fuels to any kind of hydrogen-based fuels. And also in the process itself, we would like to recirculate. So the main idea over here is carbon recirculation. So converting the CO2 from the exhaust gas as the CO, and then CO also can be utilized as the fuel, and also some like for the iron or steel making process, it can also be the reducing agents. So now we are also working for any kind of like electrochemicals or energy storage technologies, especially for the solid state battery, and also for the materials or microscopic structural optimization for any kind of electrolyzers or any kind of fuel cells. Okay, so our research is basically come from this idea. So what we call is that we are much more focusing on the non-carbon based secondary energy resources. And when we are talking about the non-carbon based secondary energy resources, then we have several options of here, including also the electricity. And then also for the chemical energy, we have, because when we are talking about the chemical energy, basically we are talking about the carbon and also hydrogens. But in case that it is non-carbon based fuels, means that we are much more focusing for the hydrogen itself, or it is derivatives, including also the ammonia, peroxide, or etc. And then also we are trying to move forward also for the metal fuels, because metal fuels also very important for the non-carbon based fuels. and also the heat itself. So our idea is basically how far we can produce the secondary energy resources effectively or efficiently from the primary energy resources. And the second one is that among this kind of available non-carbon based secondary energy resources, how far actually we can mutually convert them, like from the electricity to hydrogen, hydrogens to heat, hydrogens to metal fuels, or etc. And then finally, the third one is correlated with the storage itself. So electricity, and also probably we are much more focusing on the hydrogen storage, whether for the short-term, mid-term, and also long-term hydrogen storage itself. So why hydrogen? I think all of you also understand well about it. So I don't want to go deeper about these ones. But in general, in our experience, hydrogen is basically very potential. But when we are talking about the storage, it's very challenging because the volumetric energy density is very low. It's only 3 watt-hour per liters. But when we are talking about the gravimetric energy density, it's very excellent. So when you're talking about the utilization of hydrogen, finally, any kind of utilization that needs high gravimetric energy density will prefer hydrogens rather than other fuels. And also another opportunity, also challenge, is about the flame velocity. Once we are combusting the hydrogen, we can reach very high flame velocity of yours. And also the ignition range also very broad, very wide over here, starting from 4% until 77%. It can be challenged and it can be also the opportunity. So in terms of the safety, it means that it's very, very challenging because it is very wide. But in terms of the flammability, it means that it is easily combusted. Okay, so like in Japan, now we are discussing a lot about the hydrogens, how far hydrogen can be, can be produced with any kind of like high economic performance or very cheap actually. But the big problem so far here is that actually how far actually we can create any kind of like more economic hydrogen supply chains. So now Japan and Australia, we are having any kind of like big research, big developments about the hydrogen productions. Coming from any kind of like brown coal in Australia is converted to hydrogens, and then the produced hydrogen is liquefied to liquid hydrogen, and then liquid hydrogens can be transported to Japan. So, but the big idea over here is that until 2020, late of 2019, 2020, the big demand for the hydrogen is still projected for the transportations. But actually after that, we changed our policy, not only for the transportation, but we really understand that the big demand for the hydrogen is for the power generation. That's the biggest one for the power generation. So we would like to replace any kind of currently running coal and also natural gas-based power generators with any kind of hydrogen-based power generators, whether it is large-scale power generation or distributed small-scale power generators. And then the second largest demanders, it will be utilized for any kind of industrial demands, including especially for the iron making, steel making, cement productions, chemical industry, or etc. Then the third one is utilized for the transportation, and for the transportation, we are not only focusing for any kind of like passenger cars like Toyota Mirai, Honda Clarity, or etc., but also another big opportunity for hydrogen utilization in transportation sector is for like ships, aircraft, rail, and other things. Okay, so there are some trends actually in some Asian countries, especially like Japan, China, South Korea. Each country has set any kind of like goal. Actually, we have also in case of Japan's, we have also set any kind of like quantitative goals by 2030, 2050. So, and also about the price, the expected price for the hydrogen actually. So we are targeting by 2030, we can import the hydrogens of about 3 million ton annually. And we would like to increase to about 20 million ton annually by 2050. And we set up the expected costs. It means that not only the production, but also including also the delivery costs for the hydrogen, means that the net cost of the hydrogens sold in Japan itself. So we are targeting to get any kind of cost of about $3 per kilograms of hydrogens. For reference, The current price of the hydrogen usually produced from natural gas is about 1.5, 1.7 US dollar per kilogram. So it is about double for that. But by 2050, we are trying to reduce it to about 2 or 2.5 US dollar per kilograms of hydrogens. So I think this is the detail of the points that I have to leave regarding the hydrogen adoptions or policy in Japan in general. So from now on, I just would like to move forward for the clean hydrogen productions using what we call as the chemical looping technology. So there are some technologies. I think all of you also understand well about the conversion technologies available for producing the hydrogens, or probably the syngas before hydrogens. So we have about gasifications, steam reforming, catalysis, or etc. And also we have also what we call not pretty new, but I think it is the history of the chemical looping technology is basically quite old, quite long. But for the hydrogen production, probably it just started 1 decade ago. And we will focus on how far actually we can not only producing the hydrogens directly, but also how far actually we can also separate the CO2 or the by produce CO2 itself. So this is the concept for the chemical loopings. So in general, the chemical loopings, this is at the left side, we have the chemical looping gasifications, and the right side, we have also the chemical looping for hydrogen productions. So in conventional chemical looping technology, whether like chemical looping gasifications or chemical looping combustion systems, basically the system has two different reactors, oxidizer and also the reducer itself. So in the system itself, we introduce any kind of what we call as the oxygen carriers. So the oxygen carriers can be any kind of like metal oxide, including like the iron oxide, hematite, or etc., calcium oxide, or etc. Then in the reducers or fuel reactor over years, we abbreviate it as the FR over years, we can have any kind of fuels, usually consist of C and also H, carbon and H. So the C and H from the fuel will have a reaction with the oxygen from the metal oxide or from the oxygen carriers. And finally, the oxygen carriers or metal oxide itself will be reduced. In case of hematite, it will be reduced to FeO, boostite, or Fe, or iron itself. And then once it is reduced, then it goes for another oxidation process using the air, using the oxygen from the air, and then it can be recirculated back to its original condition, which is the hematite. So we can produce back over here the Fe2O3, while we are releasing the unreacted oxygens and also nitrogens from here. So it means that in the reducer or fuel reactor, we can avoid any kind of nitrogen oxygen over here. So we can produce the CO2 over here. While in the chemical looping hydrogen productions, we add a single reactor after the reducer or fuel reactors here. We call it as the steam reactors, or so usually for the hydrogen production, usually we call it also the water splitting process. So in case we are utilizing any kind of hematite, Fe2O3 as the oxygen carriers, means that in the fuel reactors, it will be reduced to Fe and also FeO or woodstite itself. Then the Fe or iron or woodstite FeO itself will have any reactions with the steam over here, with the oxygen from the steam for any kind of partial oxidations. Then we can produce the hydrogen over here. So the hydrogen is produced from the steam reactor. So that's why usually also this process is called as the water splitting. And while this CO2 actually is CO2 and also H2O is produced from the fuel reactor over here. So that's why in case of the chemical looping hydrogen productions, we can produce the hydrogens while we are spreading the CO2 simultaneously. And then it is similar also with the conventional chemical looping gasification or combustion over here. The produce the reacted Fe and also FeO will have reaction with the oxygens from the steam over here, and it will be oxidized partially to magnetite or Fe3O4. And then the Fe3O4 will be completely oxidized using the oxygen from the air, and it will be return back to the Fe2O3 or hematite itself. So the process, the oxygen carriers is recirculated over here. So that's why we call it as the chemical looping process. So this is the detail actually. So, but I don't want to repeat my explanation again. So the focus of the research we are doing now, because I think chemical looping although seems to be promising for hydrogen production or clean hydrogen production, because we separate the CO2, and in case that the fuel coming from any kind of like biomass, any kind of renewable sources, means that we can have any kind of negative CO2 hydrogen productions. But in case that it comes from any kind of like natural gas, coal, or any kind of like fossil fuels, means that we can have any kind of zero or clean or minimally carbon-free hydrogen productions. But actually, because as I also showed previously, we have three different reactors, and also we are dealing with what we call the metal oxide as the oxygen carriers. The reaction is very, very complex, and the controllability also another challenge actually. And when we are dealing with the, with the oxygen carriers, we can have very good oxygen carriers, but the problem is that also the cost. Or probably we can utilize any kind of like iron oxide base or hematite or etc. But the problem is that the performance, the conversion rate, or etc., is basically pretty low. So we are dealing with several challenges for the chemical looping technology for the hydrogen production over years. So in our study, we are now focusing on several aspects of research, including also how far we can try to clarify the mechanisms over years. And also in case that we are dealing with the biomass usually it also deals with any kind of like tar or char problems. And then also the lifetimes of the oxygen carrier sometimes also another challenge for all of us. And then, as I mentioned, is that it has three different reactors, and when we would like to control it, it's also another challenge actually. We can imagine like the recirculated gasifications, fluid aspect or etc. Usually also that's pretty challenges. And now we have two different reactors over here. So it means that the controllability also becomes another issue to be tackled down. And okay, then we are also collaborating with some institutions in Japan and also in other countries for tackling down several problems correlated with the chemical looping hydrogen productions, starting from the performance enhancements, how far actually we can have very good, very excellent hydrogen oxygen carriers, metal oxide, to have any kind of high conversion rate, longer lifetime, etc. And also in case that we can clarify the mechanism during the reaction, especially in the reductions process. I think that's also another good point. And also now we are developing a kind of cold model and so hot models for designing the optimized reactors. Especially if we are dealing with any kind of like biomass, means that we are also dealing with not only with the solid one, but also how far we can have or facilitate a good or sufficient residence times during the reduction process for the biomass itself, while also we can reduce the tar formations. And also finally, also how far we can have a very excellent economic performance. So technical economics and also environmental investments policy, I think that's also very important when we would like to broaden the applications of the chemical looping in the future. So when we are talking about the oxygen carriers, this is the big challenge. We can have very good oxygen carriers, but the problem is that the artificial one is also very expensive now currently, and we can have any kind of like much more economic oxygen carriers, but like FeO or Fe2O3 hematite or acid. But the problem is that, as I mentioned previously, that the conversion rate is also very low. And sometimes the reductions are also very slow actually, and stability sometimes also another challenge. So you could imagine it's like in case that we use hematite supported by alumina over years, we can imagine it's like in the first one, it is when we use any kind of new oxygen carriers, the process like this one. But when we have like 10 cycles, the actually the performance drops significantly. And also like for the DGDTA, also we can confirm over here is that the transportability of the oxygen itself also reduced significantly. So in our research, actually, how actually we would like to improve the performance of the oxygen carriers over here. There are some methods actually. There are some methods that are not explained also over here, but in our research, we are much more focusing on 3 different methods. The first is about the dopings. So we are doping with or mixing also with other doping mixings with other materials, including especially the intermediate metals, including like copper, nickel, or etc. And also now we are our PhD students are also working for combining with the perovskite structures, LZF or etc. And then also to improve the surface area, we can also combine with the any kind of mesopore structures, and also to reduce actually the total cost for the chemical loopings systems. Then we can also adopt any kind of natural oxygen carriers, including like the ilmenite, etc. We are also working with several institutions in some countries actually to explore any kind of potential natural oxygen carriers. But the problem is that usually the natural ones usually has any lower performance compared to any kind of artificial one. So the big challenge over here is that how far we can improve the performance of the natural oxygen carriers to be much more competitive with the artificial ones. And so finally, we can also reduce the total cost of the chemical looping technology itself. So we have done actually some experimental and also simulations study, numerical study using any kind of density functional theory to clarify this one. For the doping itself, our PhD student also has done research correlated with the copper dopings over years. And we could see that by dopings, although small amount of the copper, we could see that the copper dop iron oxide or hematite of yours it is much more reactive compared to the normal Fe2O3 itself. So we could see over years that the reactivity has been increased well. But we need also to be careful over here. Once we increase the ratio of the copper during the doping itself, sometimes copper also leads to the agglomerations, sintering. So that's also the things that we need actually to consider when we are trying to doping the copper and any kind of intermetallic materials to the oxygen carriers. For the reference, usually for the reductions, the temperatures is about 800, 950 degrees Celsius. So that's pretty high. So sometimes some metals actually sinter at that temperatures. So that's why in our case, actually how to minimize the amount of the doping materials like copper, nickel, or etc., while we are trying to improve the performance of the top oxygen carrier itself. So, but as we could see over years that although we drop with the small amount of 1% of the copper over years, we can get also pretty competitive or pretty excellent conversion rate compared to the original hematite, and also compared to the largest copper ratio actually. So we have also done simulations using DFT and also experiments and confirmed with the XPS. And our study showed that we can classify the oxygens in the oxygen carriers like Fe2O3, that the oxygen itself can be classified into the lattice oxygen and also the adsorbed oxygens. And you can imagine it's like in case that we drop with the copper over years, we can reduce the amount of the lattice oxygen while we are increasing the adsorbed oxygens. What we can get over here is that the energy actually for the lattice oxygen is higher than the adsorbed oxygens. So in case that we would like to release the oxygen from the oxygen carriers, we are preferring for having a larger ratio of the adsorbed oxygen. So I mean, we can reduce the energy activations for the reaction itself. And also, this is also confirmed by using any kind of like space data over years, by by doping the copper to the oxygen to the hematite itself. We can get any kind of like, and the binding energy over years for the atoms of oxygens is increased compared to the lattice oxygen itself. And also we can understand that well that the doped ones, the copper top iron oxide, is basically can reduce the oxygen vacancy formations. So by these ones, finally, what we expect is that it becomes easier to release the oxygens, and also it can improve the enhance in the catalytic reactions, and finally also we are expecting that it can increase also the reactivity itself. So another research is correlated with the not only doping but also mixing with the perovskite structures. In this case, we use any kind of LSCF with lanthanum, strontium, cobalt ferrite over here. So what we expect over here is that how far actually we can have the MEAC influence. So what we expect from here is that by adopting any kind of materials that can facilitate any kind of mixed ionic electronic data over here, we can have any kind of like much more better oxygen ion exchange in this case. And in our study, actually, finally, when we can have, we can improve this kind of, we can facilitate much more better oxygen ion exchange. Finally, also we can reduce the energy activations during the reaction itself, especially during the reductions process. So from this one, finally, it can be also by the experiment itself, we can confirm that it can also prevent any kind of agglomeration, which is actually very important in our research, because we would like to avoid any kind of agglomeration during the fluidizations for the, especially during the reduction, also the oxidations or the reaction with the steam itself. And this is also some experiments we confirms the existence of the lanthanums, strontiums, cobalt, iron, or acid over years. And then okay, we have also by doping or mixing with the any kind of perovskite materials, we can have much more stable performance of the oxygen carriers over years. So the oxygen's transportability can be maintained well for years based on the TG experiments over years. We can confirm over years. And also from now on, I just would like to, I think I still have about 10 minutes, something like that, right, Siming? Right. So
Yeah.
in the rest 10 minutes, I think I just would like to introduce some applications of the chemical looping technology, especially for the hydrogen productions and for the system levels. And we have done several research or develop also some processes or some systems for utilizing the chemical looping hydrogen production for years. So our research also correlated with the ammonia productions, methanol productions from any kind of biomass. So in case of the ammonia itself, then we can produce the hydrogens, which is very important for ammonia synthesis. So we can produce the ammonia using the hydrogens produced from the biomass, while also we are capturing the CO2 over here. So we can produce clean hydrogens, or in case that comes from the biomass, means that it is CO2 negative ammonia productions. So our systems, after integration itself, it can show very pretty high energy efficiency and also exergy efficiency. So we can have about more than 40% of the exergy efficiency, while for the energy efficiency, it shows about 55, as I remember, that's 55, 57%. And then we are also, we have done several research related with the utilizations of chemical looping for the methanol productions. So in our idea is that when we would like to have any kind of like carbon captures, we are expecting that by capturing the CO2, and then also we can convert it to any kind of methanol. Methanol then can be converted further to any kind of olefins, and then olefin can be converted to any kind of can be produced. It is very important materials for producing any kind of like polymer or etc. Means that once we can produce any kind of polymer, means that the lifetime of the carbons itself can be much more extended compared to just convert the CO2 to any kind of like fuels, methanols, and then methanols will be utilized for any kind of like fuel or etc. So it means that the carbon lifetime will be very short. So we have done also several process design for adopting the chemical looping technology for methanol productions over years. Whether it can be assisted by any kind of solar thermals or any kind of solar energy over years, or it can be any kind of standalone process without any kind of assistance or solar energy assistance over here. So we have done several research on that. Why finally we need any kind of like, in case that we can tandem together with any kind of like solar energy, especially for the solar thermal, it will be really nice because we can improve the hydrogen production's efficiency. So basically, like I think all of you also can understand well that the reduction process of AES is basically the endothermic reactions. And the partial oxidations using the steam and also the oxidation using the air for years is basically exothermic reactions. So we are expecting that the heat generated during the exothermic reactions can be utilized for the reduction process over years. But the problem is that it can self-sufficient. But the problem is that the produced hydrogen over here will be very small. So our idea is that in case that we can tandem or combine together with any kind of like solar energy, and solar energy can be utilized whether for the direct reductions over here, or it can be also it can heat up any kind of like the oxygen carriers here. So it means that it can supply the heat, additional heat for the reduction over here, because reduction over here is very, very endothermic reactions. So it means that we need any kind of additional energy from outside. So the amount of the hydrogen over here can be improved significantly. Okay, so we have also drawn or designed several processes dedicated for the solar-assisted chemical looping hydrogen productions. And we have combined, or we have designed several processes, whether it can be any kind of like solar assisted, which is dedicated only for the chemical loopings, or also it's also utilized for the power generations or etc. And then also we have tried to compare with the conventional systems utilizing our chemical looping technology also, but it's not combined directly to the chemical looping process over years. So the result shows that by combining the solar thermal energy directly to the chemical looping process, especially the reducers and also probably the after the oxidizers, I can get much more hydrogen productions over years, which is probably 25% or 20% higher compared to any kind of like, in case that we don't integrate directly the solar energy into the chemical looping process itself. And also we have tried to also develop some processes for clean steel makings actually. So as I mentioned previously, that for the steel makings, our approach, there are two approaches that we are developing currently. First is we would like to replace the currently utilized cokes or coal-based steel makings using any kind of like non-carbon-based fuels, especially the hydrogens. And the problem so far here is that in case that we utilize the hydrogens, the reductions of the Fe2O3 or iron ore to the iron itself is basically endothermic reactions. That's pretty different in case that we use the cokes or the carbons. in case of cokes or carbons, the reductions process from the hematite to iron is basically exothermic reactions. So in case that we are adopting the hydrogens for reductions of the iron ore to the iron itself, finally we need additional fuel for maintaining the temperature itself, because it is the endothermic reactions. So finally, also, I think in the future also, we still need any kind of carbon to cover this kind of combustions or high temperatures conditions, and also for any kind of carburization process, because for the carburization process, finally, also we still need carbon itself, like to create any kind of FETCs actually. Otherwise, the produced irons will be very, very soft. So we need to harden it using the carbon itself, and we can create this kind of Fe3C using the CO or any kind of carbons itself. So in our systems, we have tried to design several different processes, whether the chemical loopings using the chemical looping gasification or chemical looping hydrogen productions. In case of the chemical looping gasification, we produce the syngas itself, and then the syngas actually, whether it can be directly injected to the shaft furnace, or probably also it can use as the, we are still utilizing any kind of like CH4 or natural gas for the carbonizations. Or in terms of the chemical looping hydrogen production, we can also utilize the hydrogens directly to the shaft furnace, and convert also the hydrogens to the using any kind of reverse water gas shift reactions over years to produce the CO for the carbonizations. Or probably for the carbonization, we still need any kind of like methane or natural gas from outside. So in our experience, finally, there's no big change over years, but what we expect is that by utilizing this chemical looping technology, we are expecting that the energy, the total energy consumption can be reduced well. As it could be seen over years that using the chemical looping hydrogen production over years, finally we can have any kind of much more better energy consumptions for which is kilowatt hour per ton produced directly to iron. Okay, I think this is my last slide actually. So as I mentioned previously that chemical looping technology is still under development actually. So we are facing several challenges for whether correlated with the reaction, whether correlated with the materials for the oxygen carriers, and also some points correlated with the controllability, with the system itself, with the economic performance, or etc. But we believe that once we can tackle down these kind of problems, chemical looping hydrogen production is very potential in terms of the total energy efficiency, because we can have a much more simpler process, because we can avoid any kind of like rewarmings and also separations processes. So it means that we can have much more simpler in process in total, and also we expect that the economic performance to produce the hydrogen itself can be much more better. So we can have much more cheaper hydrogens produced from any kind of fuels, including also solid, liquid, and also gaseous fuels. And also, as I mentioned previously, that we need actually to extend further the utilizations of the chemical looping technology, especially for the various applications actually. And I think coupling the chemical loopings technology, probably not only limited to chemical looping hydrogen productions, to several different processes, industrial processes. I think that's also very important in terms of the decarbonization for our industrial sector in the futures. I think that's all from my side. Thank you very much for all your attentions. So in case that you have any questions or some points to discuss, I will warmly welcome for all of you. Thank you very much.